So in this video, I'm going to give you a brief introduction about even and odd functions specifically pertaining to calculus. So first I want to just define what an odd function is. An odd function by definition is when I plug in a negative number, I get the exact same answer as if I plugged in that positive number, except for the sign is different. So for instance, if I were to plug in -2 and get +3, then if I were to plug in +2, I would get -3. So that's how an odd function works. It's plugging in some negative number and getting an answer. And if I plug in the positive number, then I should get the exact opposite answer. By this definition, we can hopefully look at some form of rotational symmetry that should occur about the origin. So what we're going to see in our picture, in our graph, is that the whole picture should be able to be rotated around the origin a full 180 degrees, and it should look exactly the same. So to help you kind of understand this, I've got a couple of examples that I'm going to show you. The first example that I have is this function y equals x cubed minus 2x. Now again, if you notice, we've got 0, 0, we've got 1 comma -1, and if I look at -1, I've got +1. So notice again, these are opposites of each other. At 0.5, that's about negative 0.85 or so, and I should have about the same answer, again, just opposite sign if I plug in -0.5. Notice we should have x-intercepts in about the same location, and the same idea follows. At -1.5, I have about -0.45, and at +1.5, I have about the same answer. Actually, excuse me, that's 0.35, not 0.45. But going back to the idea of rotational symmetry, what I did was I actually took the picture and I rotated it 180 degrees around. Again, I rotated it all the way around, centering around the origin. And if you notice, the picture looks exactly the same, whether it's right side up or upside down. Okay? And so that's my first example, is that y equals x cubed minus 2x. I have another example that I'll share with you guys now. It's y equals x times cosine x. Again, we've got this point 0, 0. We also have a few more. Right here at about 1.75 or so, we have an x-intercept, and we have another one over here at about -1.75. At 2, it looks like our point is right about there, which is, what is that? That should be about 0.8, negative 0.8, excuse me. And I'll have the same thing, only just opposite sign in the other direction. At about -1, we are right about there, which I'll say is probably about 0.5. Excuse me, at -1, it's negative 0.5, and at +1, it's about 0.5 positive. At 4, we have a point over here, and that looks like it's probably about -2.6 or -2.7. And if I look at -4, I'm going to have positive 2.6 or 2.7. So like I said, we're hopefully noticing that if I go over here to the right and then up, it's going to come over to the left and then down the same amount. So that's kind of, again, the rotational symmetry here. I did do the same thing with this example, so hopefully you'll notice that here's the original, this is the normal view, and then I turned it upside down, and the graph itself looks exactly the same. It kind of comes up, goes down, goes back up, comes back down. It has that same exact wavelength pattern. It's almost like you wouldn't even notice the difference, besides the fact that if you look at these numbers, they're upside down. So now that I've kind of mentioned, a couple of examples of these, I wanted to kind of give you a quick guide as to how to identify what an odd function is, or what it would look like. Well, if I have a polynomial that's going to be an odd function is going to have only odd exponents. And so I'm going to go back and talk about that example I had before, my very first example, and I'll show it to you again. It's that y equals x cubed minus 2x, okay? Well, if I have y equals x cubed minus 2x, that's 2x to the first, so all of my exponents are indeed odd. if I were to talk about rational functions, what we would be looking for is we would be trying to have an odd polynomial over an even polynomial, or we could have an even polynomial over an odd polynomial. So those are good examples of odd functions. For example, I could have x to the first, which is odd, over x squared minus 4, which is even. That's a nice, pretty looking odd function. There are lots of trigonometric functions that are odd. For example, sine. Its corresponding one is cosecant. We also have tangent, and we also have cotangent. These are all odd functions. Now, I'm going to mention to you they're odd in their original form. Depending on the transformations you do to them, they may no longer be odd afterwards. Another example that I can give you as far as operations is this one. So in this case, what I have is x to the first times cosine x. Well, cosine isn't actually an odd function. But so what I can do is I can take an even function and I can multiply it by an odd function, and we're still going to have an odd function. And the order being reversed would still do the same thing, kind of like what I had up there with the rational functions. I will also mention that if I add two odd functions or if I subtract two odd functions, we'll still get an odd function. I think there's one more thing that I want to mention to you, which is about cube roots. Now, the cube root of x, which is x to the 1/3, is an odd function. However, counterexample I have for you would be the cube root of x squared. Now, that's x to the 2/3. That is not an odd function, but I think the kind of giveaway there is the 2 instead of the 1. So if I were to go back and do something like the cube root of x to the 5th, which is x to the 5/3, that is, again, an odd function, okay? Now, there is one little tidbit of information that's really important in calculus having to do with odd functions, and it's the definite integral. Now notice my bounds on the top and the bottom are the same number, just opposite signs. And right here, I'm going to plug in an odd function as my integrand. What I should always get when I do this definite integral is the same number every time, and it's always going to be 0. Now, for instance, if I were to look down here at this example that I have, this y equals x cubed minus 2x, and I were to try to do the integral from -1 to +1 of x cubed minus 2x dx, then what that means, what that represents, is this positive part from -1 to 0 and all of this area in between. But then I also have this part from 0 to +1 and all of this area in between. Now, this part on the left is positive because it's above the x-axis. But this part on the right is negative because it's below the x-axis. And because of that rotational symmetry, these two positive and negative parts are exactly the same, which means that I should always get 0 when I combine them. Now, I've talked about odd functions. It's time to talk about even functions. So the definition of an even function is very similar to an odd function, only instead of getting a function or a value of the opposite sign, it's going to be the same sign. So for instance, if I were to plug in -2 and get +3, then if I plugged in +2, I should also get +3. Notice no sign change there. And instead of having rotational symmetry, this has reflection symmetry about the y-axis, okay? And I think it'll help if we go ahead and look at our example. So again, I'm looking for reflectional symmetry. So something like folding it in half should show us what it looks like. Now, my first example is this x squared minus 5 function. So my line of symmetry is actually this y-axis. And if you notice, on both sides of this y-axis, I have the exact same point. So I've got my vertex down here at right about -5, And then here at about 1, it's -4, and at -1, it's -4. At 2, we've got right about -1, and -2 is -1. So that's kind of what we're looking at here, is this nice symmetry on both sides for these points, okay? And I'll go ahead and show you example number 2. Example number 2 is another interesting function. So in this case, I have the absolute value of sine x. Now notice again, I have this beautiful axis of symmetry here. It's a nice friendly axis of symmetry. So that notice I have this point 0, 0, and if I look at both sides, that's probably 0.75 up there for +1 and -1 x values. It looks like right about here at, I'm going to guess that that's probably pi/2 and -pi/2, that we have a maximum at +1. And we also have another x-intercept down here just past 3 and -3, which is, I'm going to say, is probably pi and -pi. So if I looked at -2, I have this point right up here. That's probably what, 0.9 or maybe 0.8. So there's another one. So like I said, we have this nice, beautiful symmetry on both sides that we get the same maximum and minimum for the x values. So pi/2 and -pi/2, we have kind of that level of, again, reflection across the y-axis. So now that I've shown you some examples, I'm going to go ahead and make sure I mention again that quick guide of how to identify some even functions. For polynomials, it's pretty straightforward. Just like when I was doing odd functions, we looked for only odd exponents. Well, for even functions, we're looking at only even exponents, okay? Now, the important part there is to remember that I had that function y = x² - 5 earlier. Well, that 5 does have an even exponent. It's x to the 0. So like I said, we're looking for even exponents there. For rational functions, we are going to look for either even over even polynomials, or we can also have odd divided by odd. For trigonometric functions, there's only 2. We have cosine x, and we have its counterpart, which is secant x. I'm also going to mention that with rational functions, I was going to give you an example. So a nice example would be something like 2 over x² - 1. So notice both of those have x to the 0s on them. So those are kind of nice and simple ones that we can do. For operations, if you multiply an even by an even, you do get an even function. What are some other ones we can talk about? We could add even and even, or we could subtract even and even that we will get another even function. And the other one that I wanted to mention that I hadn't mentioned up here, we saw a nice example on example 2, was the absolute value function. As long as I don't really do a whole lot to change where the vertex is, because notice in this case my vertex is at x = 0. So as long as I don't shift it left or right, an absolute value function is a great operation, or a great function that we could do that is an even function. I do want to point out that notice, even in this situation, the sine of x function was an odd function, but I made it even by putting absolute values around it. So that's another neat little operational trick that we can do there. Finally, again, same kind of idea. We want to talk about the definite integral here. Well, the difference is that with this definite integral, again, we have the opposite bounds. So same number, just opposite signs. What we can do to simplify things is I can take the integral from 0 to that number a of f of x dx, and I can multiply that by 2, and it should give me the exact same answer. So I kind of wanted to come back and give you a neat little demonstration of that. So for instance, if I were to look at this absolute value of sine x, the integral that I could probably calculate, again, I'll just do a nice easy one. So we'll do from -pi/2 to +pi/2 of that absolute value of sine x dx. What I can do is I can split that up, and I can do the first one. So we'll come over here, like I said, to pi/2, which is right about there. And so the first one, if I look at the positive side, is all of that. And if I look at the negative side from, I went a little too far, right about there, there's the negative pi over 2. Write that down, negative pi over 2. There's the positive pi over 2. If you notice, again, that symmetry makes it so that both of these are the same size. Well, in this case, this part is positive because, again, it's above the x-axis. And this part is negative because it's above the it's positive because it's above the x-axis. So in this case, they're going to have the same sign. They're both positive or they're both negative. So that means that I can just take one and double it, and it gives me the correct answer here. So like I said, what we could do is we could take 2 times the integral from 0 to pi over 2 of the absolute value of sine x dx, and we should have our nice pretty little answer right there. 2 follow-up questions that I wanted to make sure I mentioned was, can a function be both an even function and an odd function? And fun fact, the answer is yes, but there's only one function that I know of that actually is like that, and it's the function y equals 0. Now, in this case, it's even, because if I were to graph this, I would just have the nice horizontal x-axis, y equals 0. And so it is symmetric about the y-axis. Again, the x-axis is symmetric about the y-axis. And the other thing is, if I turn it upside down, I still have the exact same function in the exact same place in the exact same way. So again, that's the only function that I know of that is both. And the other question that I have is, can a function be neither? And the answer is also yes. We can have functions that are neither. I'll give you a nice easy example. Y equals x squared plus x minus 4. So notice in this case we have a mix of even and odd exponents. So I've got x to the second, which is even. I've got x to the first, which is odd. And I've got x to the 0, which is even. So when I have a mix of exponents like this one, we will have a function that is neither even nor odd, because it's got a mix of both. So not going to have that level of symmetry that I want, and it's not going to fit the definitions. Hopefully that helps you guys out in understanding even and odd functions and gives you some nice little tricks about how to calculate definite integrals maybe a little bit faster, so you don't have to spend as much time doing calculations. I hope you guys have a great day.